In this section, 1.3, inclined planes, we're going to be looking at situations where we have an object which we will model as a particle on some type of slope, which we call an inclined plane. So to solve problems involving inclined planes, it's usually easier to resolve parallel and perpendicular to the plane. So resolving, that's doing Newton's second law, and usually we do it parallel to the plane and perpendicular to the plane. Not every single time. There are a few situations where that isn't the most efficient method, but for the vast majority of the time it is. In all questions, make sure you draw a clear force diagram and label all angles clearly. Make the diagram large enough for you to add extra information such as velocity as you proceed through the question, and a clear diagram can help gain more method marks if your working out isn't completely clear. So there's a couple of key points here. Number one, the weight of the particle will always act vertically. That will always be true. The weight won't act in a direction such as this, because that's not vertical. It will always act vertically. So the weight vertically straight down. Please remember, if the particle has a mass of m, then the weight will be m times g. So weight, which is a force, comes from doing the mass multiplied by gravity. So the weight will always act vertically. Secondly, the normal reaction force will always act perpendicular to the surface. That's because the word normal in this context means perpendicular. Just like in coordinate geometry where we have tangents and normals, tangents and normals are perpendicular to each other. Once again, the word normal meaning perpendicular. So I'm going to draw the normal reaction force here. It will be perpendicular to the slope. So it won't be vertical. It won't be straight up. Nope. It will be perpendicular to the slope. I'm going to label it R. R for reaction, not resultant. R for reaction. Now you might get other forces pushing the object up the slope or maybe down the slope. Later on we're going to look at friction as well. Friction, which always tries to stop motion happening. Those forces might be included. Before we move on, if this angle here was alpha, then the angle I'm labeling now on the diagram is also going to be very useful to us. If we do some geometry, the weight is vertical and this is a horizontal line here, so that we have a right angle here, which makes this angle here 90 minus alpha. And because the normal reaction force is perpendicular to the slope, then this is a right angle here. So those two angles together make a right angle. Therefore, we know the angle here is also alpha. That was also alpha. Let's move on to example 1.3.1. A block of mass 12 kilograms slides down. Down is a key word there. I'm going to highlight that. A smooth slope angled at alpha degrees to the horizontal, where tan alpha is 3/4. Step 1, draw a force diagram to show all the forces acting on the block. If that wasn't part A of the question you were doing, you'd do that anyway. So drawing a force diagram is the first step, whether the question asks you to or not. Part B, find the magnitude of the normal reaction of the slope on the block, and finally find the acceleration of the block. Another important word here is the word smooth, which means there is no friction on this slope. Very soon in this chapter we will look at examples where the slope is not smooth and therefore there will be friction acting as well. But for this example there is no friction. So part A, let's draw the diagram. So I'm going to draw, well, didn't mean to do that. Let me just change. So here we go. This is my slope. And I'm going to draw a horizontal line like in the diagram above. I'm going to put an object. It says a block, it doesn't really matter what it looks like on the slope. There we go, I've tidied up my block a little bit. We will model that as a particle, we always will at A-level mechanics. That means, when we say we're modeling it as a particle, that means we are ignoring its shape. We don't care about what its shape is. We're modeling it just as a single point mass. Right, so it has a mass of 12 kilograms, which means it has a weight of 12 times g. And for the Edexcel Pearson exam board, we use g is 9.8. So that's 12 times 9.8. You could turn it into a number, but I prefer to leave it as just 12g. So very importantly, that weight is vertical. Now the normal reaction force, which will be perpendicular to the slope, I'm going to label R. And that is the force that happens when two objects are in contact with each other. So the block feels the surface of the slope pushing up on the block. And that is it. There are no more forces acting. It's smooth, there's no friction. That is it. So don't include some extra phantom force that doesn't exist, pushing it down the slope. We haven't been told about any more forces. That means they don't exist. So have a think just for a few seconds and pause the video if you want to. What is it that's actually causing this block to slide down the slope? What is it that's causing it to slide down the slope? Pause the video if you need to and have a think. Okay, so the thing that is actually causing it to slide down is the component of the weight which acts parallel to the slope. In a moment in part C, we are going to resolve parallel to the slope, and you'll see the weight does have a component acting parallel to the slope, and that is what causes it to slide down. It's not, there's no extra forces acting, it is the component of the weight which causes it to slide down the slope. So that's it for part A. However, I'm now going to put the angle on the diagram. It's sloped at an angle alpha to the horizontal. Always read that word very carefully. Sometimes it'll say alpha to the vertical. In this one, it's alpha to the horizontal. So the horizontal is like the horizon. It goes from side to side, so across, that's the horizon, horizontal. So this angle here is alpha, which means, as I said earlier in the video, this angle will also be alpha, and that will be useful to us when we start resolving perpendicular to the slope. Now take a look at how we've been given alpha. We haven't been told alpha straight out, we've been given tan of alpha is 3/4. I'm going to highly recommend that you don't use inverse tan or arctan and work out alpha. It's much simpler to do the following. So draw a right angled triangle where alpha is one of the angles, and remember that tan is opposite over adjacent. Opposite over adjacent. So that means the opposite is 3, the adjacent is 4. You might recognize these numbers, possibly the first right angled triangle you ever did Pythagoras with possibly had sides of 3, 4 and the hypotenuse of 5. Of course, if you didn't recognize it, you can just work it out using Pythagoras. Now from this diagram, if I needed sine alpha, I can just look at the diagram. Sine is opposite over hypotenuse, so that's 3/5. So sine alpha is 3/5. And if I needed cos alpha, again I can look at the diagram, adjacent over hypotenuse, that's 4/5. Much neater than doing inverse tan and getting a really horrible decimal. I'd always recommend you do that. It might seem like more work the first time you see it, or the first time you do it, but trust me, it is worth doing. It keeps things nice and neat and tidy. Right then, part B. Calculate the magnitude of the normal reaction of the slope on the block. In other words, find R. So I'm going to do Newton's second law, which is the same as resolving, perpendicular to the slope. So a little diagram here is telling the examiner what I'm doing, N2, they will understand that means Newton's second law. And this little diagram, an arrow and a right angle, that is clear to the examiner that I'm resolving perpendicular to the slope. So here we go, R is pointing in that direction already. So that's just R, that does not need resolving. However, the weight, that does need resolving into the direction that we are working with. So it needs rotating through an angle of alpha, which means it's going to be cos alpha. And then it's pointing the opposite way to my direction, so I need a minus. If you need to practice resolving forces, then please return to the earlier videos and the earlier examples in this chapter. That will be minus 12g cos alpha. That's the resultant force perpendicular to the slope. So all of that is the F in F equals ma. So the mass is 12, and the acceleration in the direction that I am currently working is 0. There is no acceleration in the direction that I'm working. There is no acceleration perpendicular to the slope. This box is sliding down the slope, so it is moving parallel to the slope. It's actually accelerating parallel to the slope, and we'll find out how much that acceleration is in a moment. But very, very importantly, there is no acceleration perpendicular to the slope. And that's one of the reasons that we resolve perpendicular to the slope, because it's actually perpendicular to the acceleration. So rearranging this, we get R is 12g cos alpha, 12g, and here I can look at my working on the right hand side. Cos alpha is 4/5. Please don't write down cos of 4/5, that's not correct. Cos alpha is 4/5. Cos alpha is 4/5. Now it's okay if you want to leave your answer as a multiple of g, or if you do turn it into a number, you need to round it to 2 or 3 significant figures. So it's either 48g over 5, you can leave it like that if you want to, or 94 newtons to 2 significant figures. If you give it to more than 3 significant figures, you will lose a mark in Edexcel Pearson exams. So 2 or 3 significant figures, no more if g has been used. That's only when g has been used. And finally, part C, find the acceleration of the block. So we know it's sliding down the slope, it's moving parallel to the slope. So on my diagram now, I'm going to put a double arrow representing the acceleration that is parallel to the slope, down the slope. So in part C, I'm going to do Newton's second law, down the slope, and parallel to the slope as well. Once again, this little diagram, and it's very simple and quick to do, but it tells the examiner what direction I'm working in, and the N2 tells them I'm doing Newton's second law. If things go wrong and you get wrong answers, then examiners need to be able to tell what you were trying to do. Was your method correct? Then you can possibly get method marks. So down the slope, 12g, the weight needs rotating through an angle of 90 minus alpha. So when we resolve, it's either 12g cos of the angle you need to rotate it through, or we can simplify that because cos of 90 minus alpha is always sine alpha. Cos of 90 minus alpha is always sine alpha. Another way of thinking of it is in part B, when I resolved, the angle was adjacent to the force. In part B, I was working perpendicular to the slope, and there the angle was adjacent, next to the force. Adjacent, think SOHCAHTOA, adjacent over hypotenuse, cos, that's why I chose cos. For this one, the angle isn't adjacent to my direction. I'm working parallel to the slope. The angle alpha that we've been given is not adjacent to that. So if it's not adjacent, then don't use cos, use sine instead, sine alpha. It just takes a bit of practice. Choose one method that works for you and stick to it, so you always get the resolving bit right. Now the reaction force R is perpendicular to my direction, therefore it will not be included in the resultant force down the slope. If you tried to include it, it would be R times the cosine of the angle you need to rotate through. So it'll be cos 90, but cos 90 is 0. That's another reason why it won't be included. So 12g sine alpha is the resultant force down the slope. And that is what's causing the particle to accelerate down the slope. So that's the F. In F equals ma, mass of 12. Don't make the mistake of writing 12g for the mass. The mass is just 12. The weight is 12g, but the mass is 12. So by rearranging this, we get the acceleration is, well, I can divide both sides of this by 12 straight away, so I don't need to put them into the calculator. So it's going to be g sine alpha. Looking at my diagram, sine alpha is 3/5. Sine alpha is 3/5, so that's 3/5 g. You can leave your answer like that if you want to, or if you do turn it into a decimal, only 2 or 3 sig fig, and that's 5.9. We need units. It's an acceleration, meters per second, to SF. And that completes our first example on using an inclined plane.